This conference will now be recorded.
MAE, mean absolute error. So simply the difference between the actual and predicted, but if you take the mean absolute difference, why, as I told you, if you take the positive or negative, some may be cancelled, but we need total difference, that can be positive or negative. So that's why modulus of differences by total number of samples. This is called MAE. And one more algorithm matrix is there, MSC, similar to this one. Before that, this is the formula MAE, same thing. Total samples. N is the number of samples for which we tested the algorithm. So this is the actual and predicted. So next MSE. What is MSE? Instead of the mod, we take the square, difference 1 square, difference 2 square. So that's why this is nothing but differences squares by number of samples. Samples in the sense testing samples. For how many samples you take these differences, that is N here. This is called mean square error. So this is also one measure error we are using. And similarly, there are other measures like MAE, MSC, which we discussed. You may take root mean square error, RMSC, that is simply square root of this MSC. And there is also another measure called R square. Based on the formula, the value of R square is between 0 and 1. Actually, it is 1 that is the best. Actually, it is 0, it is not a good value. So R square, we may decide, okay, 1 is a good, but here the MAE, MSC, RMSC, there is no standard value. So we will compare. For example, in the previous result, they shown MSC as a 1200. Okay, in your experiment, you show MSC as a 1000. It is good. So there is no fixed value, which is good. Generally, it is an error. So if the value is less, it is good. But there is no standard value for the MSC or RMSC. So we will try to see these experiment. Already we loaded the data set, the data set which we discussed morning, the data pre-processing, which is nothing but the insurance data set. Here, see, here we need to predict the charges. So medical charges you need to predict based on these independent variables. So per year, how much medical cost you need to do. So that can be predicted here. So this is a number. So that's why this is a regression problem. So I divided and I applied. See, the same thing for simple linear regression. There we are having one independent variable, but for multiple linear regression, more independent variables. But the method is same, and I also applied the same predict method. Now see here y predict and y test. So here the actual value is 9724 and the predicted 11,000. The actual is 8,500. Predicted 9,900. But the difference came here in the training data. X test you will see here. This is the input data actually for first row input data, that is so and so age and so BMI value having number of children one. The actual value is medical cost needed is 9724, but our algorithm predicted 11,448. In the previous case, it is only a single independent variable, but here more than one independent variable. That is only the difference. The remaining is same actually. It can be a simple or multiple. But here you can also do a single prediction. That means, okay, this is a data set, actual data set. I want to predict the medical cost for a particular age, particular gender, a male or female, and we were given a specific BMI value, having specific value of children, whether he is a smoker or not. That means only single input you can give. That means new input. That is not in your test data, but you want to check it. You can do a single prediction. See, C is equal to R dot predict of. You need to give all those values. See here, what is the first one? Age. But after changing, after applying encoding, what happened? This is the shape of the data set. So here first, what is this 10? These two represents. Open the data set and see what are those two. Gender, that can be gender, because there are two. Those two are nothing but these two. One not encoded. And this one is the smoker. So this is smoker no, smoker yes. So this is gender female, gender male. So in this way, you need to give the input. See here, I had given 10 means, what does it mean? 1 is the female and 0 is the male. That means a female person. And second two represent no and yes, as I told you, not a smoker. These two represents a female and these two represents not a smoker with age of 53 BMI 45, having 3 children, what is the medical cost needed? We need to predict. This is a single prediction. So you can do it. The value is 17,335. That means for not only testing data, you want to test it for a single sample also you can do. But before giving the input, you need to check this, the final format before applying the algorithm. So before applying the algorithm, the data set is in this format. So you need to give the data in this way. That's why I told you, you need to know what is 1, what is 0. You need to know here. You need to know this 1 0 indicates female S and male O. This 1 0 indicates second one smoker, not smoker. So in this way, you can also make single predictions. As I told you, the measures like R square. So these are the packages used in Python. R2 underscore score is for R square. Mean underscore absolute underscore error is for MAE. Mean underscore squared underscore error is for MSE. And root mean squared error simply square root. So you can also see all these variable values. See here, R square is 0.79. As I told you, its value is between 0 to 1. 1 is good. Of course, it is not exactly same. You may think like this 79%, but don't think it is 79%. The actual meaning is not like that. But you may think like that because the values are between 0 and 1. 1 is best, as I told you. So it is 0.79. It's like 79% like that. But this is not an accuracy. But MAE and MSE and RMSE are the values you can compare. You don't know by saying this 39 MAE, it is good or bad, you don't know. You take the same data set, apply one more algorithm, and see if you'll get less value than this value, that algorithm is good like that. Or in the previous studies, they get 4,000 value, now we get 3,900, this is good. Like that only, but there is no predefined values for this mean squared error, mean absolute error, whatever it may be. Error, there is no predefined value. Error 0 is good, but error 0 is impossible actually. Okay, so this is a multiple linear regression model. So all these measures are also same, and R square, as I told you, is a formula between 0 and 1. Actually, not only these measures, there are other measures also. A p value. We calculate p value for each and every feature. If the p value is less than 0.05, actually that is a good feature. If the p value is greater than 0.05, that feature is not so much useful for identifying your dependent variable. Okay, so you need to see the feature values by p value also. Okay, now coming to the other measures, there are also other measures like regression coefficients. Coefficients value means how much quantity is changing based on the dependent variable. We will see standard error. This is also an error measure from the actual and difference. The error is low, that is good, error is high, not good. And if you divide this regression coefficient by standard error, you will get t value. So regression coefficient gives the magnitude. For example, both the independent features 1 and 2 are good, but in those two, which is having more effect? So that is nothing but the coefficient. Okay, we will try to see all these measures also. And coming to backward elimination, as I told you, backward elimination means, for example, the problem is given for you, and you need to find what is the best independent variable. Of course, there are 10 independent variables which affects the dependent variable, but you need to identify the best independent variable or best set of independent variables. You need to apply this backward elimination. So what is backward elimination is, first we start with the whole list. In this case, for example, we start with 6 or 7 variables. I will take all 7 and I find what is the worst variable, not best variable, what is the worst variable, and remove it, and next worst variable, remove it, and finally ended with only the best features. What all these features? The best features means nothing but the features which are affecting more my dependent variable. Those are the best features. How to do this? For doing this analysis, we use stat models package.api, not sklearn actually. For this view, we use another model called as stats models. We need to add once actually. Why we need to add once, I will show you, explaining the code. But after that, I need to add this once. And after that, see, I have taken all the variables here. And simply I am using OLS. OLS is a function. It is nothing but ordinary list squares in which you need to give x value and y value. And by giving the summary, it shows which is an important variable, which is not important variable. So then why I need to add ones also I will show you actually before going to the implementation. See, coming to the back to the your linear regression, multiple linear regression equation. See here, what is this equation? Y is equal to b naught plus b1 into x1. But here b naught into 1 is there. After that, b1 into x1, b2 into x1. So here b naught into 1. That 1 we need to manually input to the algorithm. That's why we need to take ones and add those ones to our program. Okay. Now I will try to show you in the Python directly. The spider I will show you how to add this. Okay. Now try to see the same code which I am using. Up to here, everything is same. Now see here, I am removing everything for clarity. Okay, so no need to bother about the remaining things. See, this is the way we are using statsmodels.api for our backward elimination. So what I have done is very simple. See here, I taken this one x underscore new, that is same as the original one. As I told you, the first two indicates these two indicates female male, and these two indicates smoker yes or no, and I added ones. You observe the first column is all ones. Why I added ones? As I shown you, b naught into 1 plus b1 into x1. I added ones. All the remaining are same features, but I put in another new variable x. But later what I have done is I simply see the result. Okay, so after pressing the summary with OLS, now you will get all these values, see this coefficient, standard error, p-value, p-value. So you need to consider the R-square is also there, R-square value, adjusted R-square. Actually, there is another measure, adjusted R-square, we will combine this. But our most of interest is p-value. As I told you, p-value is greater than 0.05, it is not good. And this first one is constant, you just ignore it. See, for this one, p-value is 0.6, it is not good. For the x2 also 0.9, it is not good. So for all the remaining 0.000, so all these four variables are good. And these two are not so much effect on the model. So you just remove this. If there are two p-values greater than 0.05, you consider the maximum value. This is 0.993. That means this second variable. Of course, what is that second, for example, okay, whatever it may be, 0 and 1, 2, 3. That is third actually, including the constant, that is third. I think yes, that is third, not second. The first one is the constant. So we need to remove that. See, this is first, second, and third. For third one, p-value is more. So I am removing the third one. What is the third one? So 0, 1, 2. So I remove 2 here. So you observe the difference between this one. I am removed that variable, writing the same 3 lines of code, copy paste it, but remove this one variable, which is not so much useful. So 0, 1, 3, 4, 5, 6. Now once again run this code. Now once again you will see the result. You repeat the process. So once again see now which is having more p-value, ignoring this first line. This one, once again it is 0.7. So that is nothing but you need to remove that variable again. That means just write the same code, and this one, the second one, first constant, second one I remove. So 0, 3, 4, 5, 6. Run again F9, and now again you get some output. And now see, ignore this first one. The p-value is 0.000. Everything is good. That means the p-value must be less than 0.05. That is the standard definition. I'm not spending much more time in p-value. We need to see some models, but all these are having good values. So these four are the good features. What are these features? You need to identify 3, 4, 5, 6 in our original data set. We will open our original data set 1, and 3, 4, 5, 6 we will see. So 3, 4, 5, 6 means these four values, number of children, BMI, age, and this smoker are not. Only this smoker S. So these four are having more effect on your model. That is the summary. So this backward elimination gives more exposure about what are the important features in your data set. Okay. Now not only this, we can also see the other measures. As I told you, coefficient. If you consider the magnitude, now for example, in x3 and x4, This is 322, this is 259. That means this feature is having more impact than this extreme, this below above feature. So that is the coefficient magnitude we need to consider. Error, coming to error, this is having more error. See, there is no thumb rule. Okay, where can I consider standard error or I can consider coefficient? No thumb rule. We need to see all, and we can justify. See, this is having more magnitude but more error. This is having less magnitude but having less error. So from error point of view, this is good because 11 is less, but for magnitude point of view, this is good. That's why you need to consider these two. So like this you can justify, but PY is important. First priority you need to consider. If the value is like greater than 0.05, you just remove that variable. And if you divide these two, you get this two value. And you can also check the R square value 0.74, like 74%. You may think like that. Okay, so this is called a backward elimination. This is very much useful in regression problems to identify the best features of your model. But of course, you can do a number of other experiments also. This is the site where you find different regression data sets. Of course, you can find in the Kaggle. All these data sets are available in Kaggle. But particularly these 10 data sets are for regression task. You can download and do. Of course, you click on this link, it directly connects to the Kaggle. Cancer, linear regression, CDC data, fish marketing, medical insurance costs. Actually, this medical insurance costs is the data set which we use now. Stock exchange, OLS regression, real estate price prediction, red wine quality, and vehicle data set, routes, life expectancy, whatever it may be. These are some important data sets. Of course, all these are available from Kaggle, but I'll put in a one website which may be useful for doing the experiments. Okay, so those are some data sets. We just move on to the next algorithm, decision tree regression. So decision tree regression is a tree-based algorithm. Up to now we see the line-based algorithm, but it is a purely a tree-based algorithm. So here we need to draw a tree for your features. Now you may have a doubt, sir. Okay, it is in Excel sheet. Okay, I will take something on x-axis, y-axis. Even though multiple linear regression, it works in a multi-dimensional way. As for simple linear regression, I told you one independent, one dependent, draw a line. The same thing applied in MLR also. But the difference is here in the place of one independent variable, multiple independent variables, error calculated, line change, the same thing happened. But coming to the decision tree, the story is different. What happened in the decision tree? You simply draw a tree. The tree is based on some measures. How to draw the tree? How to construct the tree? That is the big question. Before going to the code is not so much difficult. We will try to see how this decision tree is constructed. So for that, we use some measure. As I told you, for drawing the line also, we consider an error measure like a least square, sum of least squares, or whatever it may be, ordinary least squares, sum of squared residuals. We call it an error one, error two, line two. Some error is there. It is good or not. How to identify the good or not? Definitely the error you need to find some measure. So similarly in decision tree regression, we use an error called as mean squared error. What is the purpose of this mean squared error? You find something and calculate error and find another thing, calculate error, which is having less error, that is good. What is that something, how to calculate? We will see, discuss next few slides, but this is the error, mean squared error. The mean squared error definition we know. This is the mean squared error. Actual minus predictor square by total number of samples. That is nothing but mean. If we divide by total, it gives the mean value. Okay. And now coming to the actual part, an example, decision tree regression example. Consider a new drug is introduced in a market for certain disease. For example, the drug is introduced and we don't know the effect of the drug. So you need to do some clinical trials. If the data is like this, for example, if you consider your data is in this format, it's okay. It's easy to okay for you to draw a line. Yes, if the data is like this, you can draw the line because all the points are in a linear fashion. You can draw the line and you can tell the value based on the input and given output. But the medical data is not like this actually. The data is like this. Why the data is like this? We can also easily you can understand. You see what is on x-axis, what is on y-axis. On x-axis we are having drug dosage. On y-axis you are having effectiveness. We know if the drug dosage is less, effectiveness is 0. That is, less drug is not effective. But if the drug dosage is more, that means you give more than the required, what happens? Then also effectiveness is 0. See here, for less 0 effectiveness, for more also 0. If the drug dosage is the correct dosage, then only it is 100% effective. So this is the scenario actually. This is the real-time picture of this medical data science. So that's why in this case, how can you draw a line? If your data is like this, it is not possible to draw a line. So the solution is here we use the trees. These regression trees are helpful here. In this case, the tree format is very much useful. So now consider the same equation, how you get this one as a root node, how you get dosage less than 14.5 as a root node. Once again, we need to see that. Okay, so for example, consider these data points only. Consider first 2 points and draw a red line between those 2 points. And now what happened? Left side of red line and right side of red line. So that is nothing but dosage less than 3. So this is at 3, for example. So if I put root node as dosage less than 3, that means dosage less than 3 means left side of red line. Greater than 3 means right side of red line. That is left child, right child. So if dosage less than 3, what is the effectiveness? 0 only, because only 1 point on the left hand side of the red line, 1 point, and that effectiveness you need to consider y-axis 0. And right hand side means you need to consider all these points. If dosage less than 3, no. What is indirectly meaning dosage greater than 3? That means all these points you need to calculate effectiveness. How to calculate effectiveness? Take all these values on y-axis and average. So see, this is effective 100%. These 4 points, these are effective 50 to 60. So how many samples are there? Total effectiveness by the total samples simplified, we will get an effectiveness. For example, you got an average of 38.8. Okay. So, but here see, this is a good one or bad one. How the algorithm identifies? Yes, once again, it calculates the error. So this is the actual. This is the predicted because the average is the predicted. So the difference. Once again, residual, we use the term. So for all the things, you need to take the differences and squares, similar to previous one here. So sum of squares, you done the error and the actual. So actual is nothing but the points. Error is nothing but predicted is nothing but this line average. We'll take an average means error. So for example, my error is 27,000 here. Now I plot in a graph like same which I explained in the morning. Whenever you get an error, plot a graph. Next, get an error, plot here, find the minimum error. The same thing. Now just move this line to next 2 points. In the previous case, first 2 points considered. Now consider next 2 points. Once again, draw a line, left side, right side. Repeat the story. Once again, calculate the error. This is the error. And next, once again, try to consider next 2 points and draw the line. And once again, left side, right side, and calculate the error. You repeat this step. These are the errors I got. And where is minimum error? This one. So this is nothing but the minimum error, and where we got error, we will check the condition where we got. But the condition is here, dosage less than 14.5. So that's why this is the rule. So here also some another criteria is used, but same story as in linear regression. We need to predict something, find the error, predict new thing, find the error, predict new thing, find the error, which is having less error, that becomes the root node. But this is only for identifying the root node. Once again, what happens? This is the root node. Now you have an idea. This is the root. You declare on left side and on right side. You can recursively apply. You fix minimum points. Okay, minimum points here 6. Okay, for example, you fix minimum point 6. Okay, left side there is no need to extend to 3. But on right side more than 6 points, we try to apply this recursively. So I applied this recursively to get this complete tree. You see what is my complete tree here. This one, this is effectiveness 100%, and this is 4.2%, usage less than 14.5. All these values average 4.2%, and this is 2.5%. That is greater than or equal to 29. Okay, and but less than or equal to 14.5. Like this, similarly, this is 52.8 between this black and green dotted line, and this is 100% effectiveness. That means this red and black points. So you can see the condition greater than or equal to 23.5. No, that means less than or equal to 23.5. That is the meaning. So less than or equal to 23.5. So here S and no, S and no only. This is the way to draw a decision tree regression. Of course, there are other methods are also. but most of them use the measure called as mean square error. Okay, this is the one of the measure used. Okay, that is the decision tree. Writing the code is not so much difficult actually. The same insurance problem I am considering because all the remaining code is same. The same story up here. Only the thing is we use another class called decision tree regressor and create an object. You can also give splits, minimum splits given, and X train and Y train. That is common. And prediction is also same as you observe. So only the class is changed. The remaining is same. So even the background details are hidden by your SQL. It will take care about all those things. But we need to know what is happening in the background. Okay, that is the decision tree regression. But we will try to apply this for a new data set. Okay, this is another data set actually, a data set from UCI machine learning repository. This is also another repository like Kaggle. UCI is also another machine learning repository. In this data set, I downloaded one particular data set. Before going to that, we will try to see what is the data set. The data set contains some 9,000 data samples of a combined cycle power plant. Actually, this is a data set related to power plant. So first we need to know about that cycle power plant, how it works. So after knowing only, you can apply the algorithm actually. But for implementation purpose, I am showing that without knowing, applying algorithm is not a good thing. So by seeing the data set, I will open the data set. It contains some features like temperature, pressure, APA, and humidity, H, and vacuum V, 4 variables, and we need to predict the energy, net hourly energy. So here the description is completely given what you need to predict. Simply given is predict net hourly electrical energy output. So energy is a continuous value number. That's why it is a regression problem. All the remaining are the independent variables. So just I try to open the data set and see the data set. So the data set is in XLSX format. Of course, you may use another read underscore Excel, or you can just save it as a CSV file. See this temperature, vacuum, pressure, and humidity, 4 independent variables, and P predicted energy is the dependent variable. All are the numbers. You don't need to apply any data pre-processing. You can directly apply the algorithm here. Okay. So we will try to apply the decision tree regression for this energy algorithm. And later we move on to the next algorithm. So as the directory changed, as I shown you, you need to set the directory and later try to import the data set. If the data set is not available, it shows like this. Maybe the data set is not in that folder. We will try to see the actual folder. The data set is not there. I will try to load it. Maybe that may be available in the other directory. I will do it. So in the regression, the data set which we use period.csv. So I change it as a power detection and save it as a CSV file. You observed that. So now paste it and now try to execute it. So now the data set is loaded. So the data set, temperature, vacuum, pressure, humidity, and energy. Actually, as I told you, it is irrelevant to apply the algorithm without studying all these features. You are applying algorithm means you must have some idea about your research problem. But for showing you the implementation part, I am using this algorithm. So decision tree regression, I applied, predicted, I applied. See, the same story happened. Whatever it may be algorithm, the implementation part in Python is very easy. Once again, you got y test, y predicted. So the energy values, these are the actual values, these are the predicted values. Okay. The same story. Once again, you calculate all these measures. See, the R square value is 0.93, which is a good above 90.9, and NAE, MSC, and RMSC. So the same way, whatever may be the data set, the same thing, and only the 3 lines of code change. That's why I explained the data pre-processing also. This is also important. This is common for almost every data set. If there are categorical features, you apply encoding. If there are missing values, you apply missing value code. but only these three lines of code change from algorithm to algorithm. Okay, so that is decision tree regression. And now try to move on to next one, random forest regression. So what is random forest regression? It is also called as an ensemble regression method. It is also called bagging actually. That means simply combining several decision trees. So
Sir,
now, hello,
sir,
ma'am.
what exactly is the difference between decision tree and decision tree regression?
Yes, ma'am. Decision tree can be applied to both regression and classification. If you apply decision tree for regression, it is called decision tree regression. If you apply decision tree for classification, it is called decision tree classification. So combinedly, we can general word we use decision trees. That means that can be regression or classification. Okay, decision tree can be used in both regression and classification. So there is no separate third decision tree actually. If whenever you are using the term decision tree means that can be a decision tree regression or decision tree classification. Any one of these. The general name is decision tree. Okay, ma'am? Hello?
Okay, sir. Yeah, thank you,
Okay.
sir.
Okay. See, one more thing is the decision tree, random forest, and support vector. These three are used for both regression and as well as classification. But we use some different thing. Of course, where we are predicting number, here we are predicting category. Something is changed, but the concept is same. Construction of tree is same, but finding the output prediction is different. So see, this is very important. Three algorithms. What are those? Decision tree, random forest, support vector. These three are used for both regression and classification. Okay, so if it is used for regression, we call it regression. If it is used for classification, we are classification. So you combine different decision trees. You apply decision tree 1, 2, 3. And what is the final thing? We need to consider all the opinions. So you average, because this is prediction, you average all these values. For example, tree 1 gives 0.2 value, tree 2 minus 0.1, tree 3.5. So you will take average this plus this by 3. So the average 0.2, the predicted value is 0.2. But if it is a classification, it takes the voting. I will explain the relation to random forest classification. Then I will discuss. This is regression. Our value is the number, so it will take the average of all the numbers by number of trees. You can change the number of trees in your formula. And that is your class argument. You can change how many trees you want. So generally, in all the regression algorithms, random forest is good. Why it is good? So we are combining more algorithms, but only single decision tree also powerful actually. As I shown you, the data set is not a linear, the medical data set. The data is in a different format, different way. Then also the decision tree handles efficiently. But if you combine more than one decision tree, then automatically random forest gives better results. But as once again I have told you, there is no thumb rule. Okay, only random forest gives better prediction. That all depends on that. For some data sets, random forest may also not give good results. Linear regression may give. So the all depends on data set. But in general, random forest is the best classifier in all regression as well as in classification also, because it combines several other methods. Okay, so number of decision trees you will take. So writing the code, I am not spending a lot of time because we will see classification algorithms also. This all the above thing is same. Only the class name change. Random forest regressor. If it is a classifier, maybe it is classifier class. Separate class is there, and simply create an object and fit. And in the parentheses, we will give number of trees. I will show you in the implementation part, and compare the performance. Similarly, for the energy data set also, we will try to do it for at least one of the data set. That students data set, or it can be the energy prediction data set, whatever it will be. We'll try to execute it. So here only the difference is we are combining more decision trees. The remaining is same. One decision tree is powerful, as I told you. If you combine many, what happened? Generally the power increases. Okay, so I am running all these a single step because this is same data set. And here, as I told you, n underscore estimators is equal to 160. You can change that 160, 180, 200. How many trees you want? How many decision trees you want? Just give this parameter 160. I have given. You can give any number. That feature can be changed as, and the remaining is same. Okay, so it will take, it is taking some time. If you increase the number of trees, it is taking some time. Seeing the results is same. We use R square value 0.96 for the same energy prediction. I think we got 0.94 for this. See, 0.93 for decision tree is for the same problem, and 0.96 for random forest. Improved, the accuracy is increased 93 to 96. Similarly, MSC is 10.3. What about the MSC? Maybe same or different. It is 18. So error is here 18 and here it is 10 because it is combining different algorithms. That's why it is called ensemble model, ensemble learning, random forest. Ensembling means combining more than one model. So you combined 160 decision trees and average all these 160 answers, and finally you predict the answer. That's why this error is less. This is once again predicted actual. The same story remains for all the regression algorithms. Actual predicted, actual predicted. Okay. So that is the random forest. Now support vector regression. Actually, we need to discuss some classification algorithm also. I will try to finish the support vector regression within less time, and once again we move on to the next algorithm, classification algorithms. Support vector regression is actually the algorithm which involved more mathematics than any other regression algorithm. We know this. What is these ordinary least squares? There is a line. We need to find errors. For that, this is the formula. But in support vector regression, what happens? Including this line, there are two lines, not two more lines, above one line, below one line. See, in the linear regression, only one line. In the support vector regression, three lines. This is the middle line. This is similar to our linear regression error line. And above and below, some another lines are added. Those are called hyperplanes actually. So now it seems like a tube. We may call it as a tube. That means this is the tube on which we are allowing errors. What does it mean in linear regression? This point is an error because it is not aligned with the line. But in this sphere, the point which is in the tube is not considered as error. That means we are giving some chance of error. Not a strict rule, you may think like that. So above this dotted line hyperplane is only error. Within that hyperplanes, that is not an error. So these red circle points, those can be treated as an error. And how to draw this above line and below line? So those lines are drawn by using some points. Once again, the data points, and those points are called support vectors actually. So based on the support vectors, we draw some hyperplanes. So above, for example, some plus epsilon, below minus epsilon. That epsilon is nothing but the distance you may take this line to this plane, this line to this plane. For that, we are using some more formulas. And not only this, we also add some more constant epsilon to, which are called slack variables and some mathematics involved. This is the summary actually. And this is the middle line, which is similar to our linear regression line. But we having some additional element chance, which is nothing but plus epsilon minus epsilon dotted line. And for drawing the dotted line, the circle points we are used, and those are called support vectors. And these points, after these are called as an errors actually. The points below this tube are not considered as errors, and this is called a hyperplane totally, and these points are called support vectors. Okay, so for implementation of support vector, the same thing actually. Only the thing is, you just put SVR. Okay. So from sklearn.svm, import SVR, and here kernel is RBF. What is a kernel? We will discuss in classification. As I told you, the support vector can be used for regressional classification because we are having some only 1 hour time, and we want the classification algorithms. There I will discuss what is this kernel, because kernel is same in both the regression and classification because this algorithm is same. So then also implementing the same way, we will get the results. Okay, as I shown all the algorithms, I am not showing that implementation. So now we will discuss some classification algorithms. So what is a classification algorithm? In regression algorithm, we are moving to this is an introduction part. In regression algorithm, we are predicting a number that can be height or weight or energy or insurance charges or GPA. All these are values, continuous values. But in classification, you are predicting a label. That means you are predicting yes or no. A student can be pass or fail, or the fruit name, or the color name, whatever it may be. Here, the output is a category. Simply, output is a categorical feature. So text. So here this is called classification. Here there are some algorithms like logistic regression, KNN, SVM, Naïve Bayes, decision tree, random forest. As I told you, the support vector, decision tree, random forest are also in classification. These three are also in regression. Okay. And the additional things are this KNN, logistic regression, and Naïve Bayes. So we will try to discuss. It is not possible to discuss all the algorithms actually, but I will try to discuss the first algorithm, logistic regression, because if you understand at least one algorithm, that is not so much difficult. KNN also I will explain. Still I will explain because KNN is not so much difficult. It is very easy. The remaining, I think I explained the concept background on the algorithms. I will try to finish some faster. So coming to logistic regression. So see, the logistic regression uses some mathematical equations. We know this. What is this? This is a linear regression. Experience and salary, we draw a line. Some equation is there. But in logistic regression, on the y-axis, we are having probabilities instead of the your actual values probabilities. Why probabilities? Here my dependent variable is yes or no, or some classes. So here 0 and 1 are pass or fail, whatever it may be. Here the probability, why we use probabilities, the answer is here not a number. The answer is a label. So that's why it comes in between the probabilities. So 0 and 1 y-axis. And the x-axis is same. So somewhat tricky, and here instead of line, we use a swiggle-shaped line. It is not a line, swiggle-shaped curve actually. Instead of line, we are having this S-shaped curve in logistic regression. So this is the probability from 0.7 to 99, like this 0 to 1. And the x-axis values are not changed, all the independent variables. Once again, on the y-axis, we are having actual and predicted, but instead of the regression numbers, we are having probabilities. So if the probability is 0.6, now you say that into one class. For example, class 1 and pass and fail, two classes. So above 0.5, we may thrown into pass class, and below 0.5, we may thrown into fail class. That is the decided. And not only 0.5, you may decide that a benchmark, it may be 0.6. Okay, only above 0.6 pass, below 0.6 fail. What is this 0.5, 0.6 is? This is the probabilities which calculated by these algorithms actually, not you. So the probability of this sample becomes this pass is that given 0.5, 0.6, 0.7, you fix that value. And actually, there are some more algorithms, not algorithms, concepts used in logistic regression. See, this first one is simple linear regression. That is easy. But here, this is a S-shaped curve. As I told you, two functions are used. This first one is sigmoid function, and the second one is called logic function. These two functions are used in the background of the logistic regression. So why we use these two functions? It will take some lot of time, but I will try to give you in a brief way. Before going to that, you will see one interesting thing here. As I told you, this is a classification technique, but still its name includes regression, logistic regression. Why its name includes logistic regression means in the background it uses the same technique which we used in regression. That means the drawing a line. So the concept of drawing a line is happened in the background of your logistic regression, and later you convert that line into this S-shaped curve with the probabilities, and you get the probabilities. But internally in the middle, you draw a line. So for that, actually there are number of functions used. Okay, so the functions used. I am taking one example. For example, we need to predict weight is given, mouse weight is given. You need to predict whether the mouse is obese or not obese. So here the category is the output is obese, that is S category, not obese, no category. These are the data points, and the weight is given as the input. For example, what I told you, the measures which we use in linear regression are different, least squares is different, but here the measures used is different. In the linear regression, as I shown you, we use squared residuals, error square, but here you use another measure called maximum likelihood. You may think like probability, but exactly not same as probability, maximum likelihood. So if there is, for example, the same story, instead of this line, you are having a shaped curve. You draw one shaped curve, calculate maximum likelihood. Draw another shaped curve, calculate another maximum likelihood. Draw third, calculate another maximum likelihood. But this is not an error. Which is having more maximum likelihood? That is the best S-shaped curve here. So that is the thing. Okay, of course the formulas may be different. The concept is same here. You need to draw more and more S-shaped curves and find the maximum likelihood for which there is a maximum likelihood is more. That is the good S-shaped curve. But drawing the S-shaped curve internally, one more line is drawn actually. The line is there actually in the background of this S-shaped curve. As I told you, this is a S-shaped curve. It is internally converted into this plus infinity to minus infinity, a linear regression curve only by using a function log of odds. So what is this log of odds? Okay, it is somewhat additional topic, but okay, I will try to finish within 1 or 2 minutes. This is the probability we know. For example, total 8 games played by the team, 5-1. We divided 5 by 8. This is the probability. But log of odds means win by other. But odds means not log of odds. First means odds. So probability means win by total. We know this. But odds means win by loss. So 5 win by 5 1 by 3 loss. So 5 by 3. This is the difference between odds. So probability and odds are not same exactly. There is a difference. But odds can be calculated. This is the formula I explained. In another way also, p by 1 minus p. That is, as I told you, 5 by 3. But how do you get 5 by 3? Probability of winning is 5 by 8. Probability of losing 3 by 8. So 5 by 8 by 3 by 8 also given 5 by 3. That means the odds formula is, first formula is win by loss. Second formula is p by 1 minus p. That is probability of winning by probability of loss. So in mathematics, this formula is used, p by 1 minus p. Okay. So if you directly use p by 1 minus p, there is no balance actually. That's why we apply log. For example, see if 1 by 6 is there, then if you apply odds function 0.17. If 6 by 1 it is 6, there is a lot of difference is there. What is meaning of 1 by 6? As I told you, 1 win by 6 loss. Here 6 win by 1 loss. So then the values are very difference is there, 0.17 and 0.6. To balance that, if you apply logarithm, so if you apply log to 0.17 and if you apply log to 6, what happened? All comes in the same range. So that's why we are using this function log of p by 1 minus p. First, p by 1 minus p is nothing but odds, and to balance that value, we apply log. And this function, where we are using this function to convert our S-shaped curve into this linear regression curve. So how to convert the formula? Here the p value is 0.5. So log of p by 1 means 0. Here 0.5 means here 0. So that is the way. Internally, here this is 0.7. That means here 1. Like this, what happened is, for every your S-shaped curve in the background, there is your minus infinity plus infinity y-axis curve with the linear regression. So what you need to do is, actually you draw a line. Okay, so I'm moving forward. See here, you draw a line first, and after identifying the best line, you need to map it back. For that, use reverse engineering. This is forward engineering, this is reverse engineering. For that, we use this function, sigmoid function. That means first you convert it into linear regression problem, and then once again convert back into this S-shaped curve problem. Here we use the function log of odds, converting into this way, and to reverse it to get our S-shaped curve, we use this sigmoid function. Okay, so there is here a lot of mathematics involved actually internally. I'm not going to discuss more because it takes a lot of time. You need to calculate maximum likelihood. This is the formula for calculating likelihood actually. So what is happening in summary? We will try to see. See, every time you need to calculate maximum likelihood. See, if there is a line, means you are imagining that there is a shaped curve. This is line 1, line 2, line 3, and finally this is the best line. For example, with less error. For that, you map it into your S-shaped curve using that sigmoid function. Okay, this is the story behind that. So why we will call it as logistic regression means it uses a regression method in the background. That's why it is a logistic regression. So as I told you, this function, sigmoid function, is used from this conversion, from this conversion to this conversion, as I told you. But once again, this log of odds, log of p by 1 minus p, is used for converting S-shape to this minus infinity plus infinity y-axis, x and y-axis. Okay. So that is the story behind logistic regression. We will try to implement the logistic regression and come back again. Now, before that, okay, we will try to see the error measurement also. Of course, now you are having how to implement the code. You are having some idea. It's not difficult for you, I think. But I think it's better to see some important measures. What are the measures we are using for classification problems? So in the regression, we know what we are predicting is a number, but in classification, it is not a number. So as I told you, if this is actual and predicted 0, 0, but don't think this 0 is a number. For example, in the place of pass, I put 1. In the place of fail, I put 0. Now, even though those are zeros and ones, those are not numbers. Those are categories only. You consider those are as categories only. Okay, you need to understand that. So in classification problem, we are having categories only. And sometimes in the place of categories, they may give zeros and ones for pass 1, fail 0, S1, fail no, like that given. So these are S and No's actually. So here, see 0, 0 means no, actual label is no, algorithm predicted no. So in the regression, we subtracted. So some medical charges actual and predicted. You subtract one from one another. But here, no to no, yes to yes subtraction is not possible. So only here the thing is 4 possible predictions are there. What are those? 0 can be predicted as 0, 0 can be predicted as 1 can be predicted as 0, 1 can be predicted as 1. So 4 possibilities are there. And these 2 are correct predictions. This means actually the student is failed, algorithm predicted as 0. Actually the student is passed, algorithm predicted as passed. So these are correct predictions. Similarly, these 2 are wrong predictions. So once again, how to calculate the accuracy? Total number of correct predictions by total predictions. So here we are having accuracy. In the regression, we used R square and errors. In the classification, we used accuracy. Not only accuracy, some more measures also there. I will explain. But this is the first and foremost measure we are using in classification problem. So accuracy is equal to total number of correct predictions by all predictions. That is correct plus wrong predictions. This is very straightforward. We calculate how many correct predictions are there because these are all yes, no's, labels, not numbers. This is somewhat easy. And we use a notation called confusion matrix. So it is also same. Confusion matrix is nothing new. In this confusion matrix, this diagonal are correct predictions. What are these TP, FP, FN, TN? The same thing. TP means true positive. That means actually is true, predicted as true. That means one can be predicted as one like that. False positive means actual is false, your algorithm predicted true. FN means true can be predicted as false. And true negative is false can be predicted as false. So anyway, only this true can be true and false can be false are correct. So when you consider this diagonal, those are correct predictions. And there, if you divide the TP plus TN, the formula C accuracy is equal to by all these 4 gives accuracy. But here sometimes the accuracy is not only sufficient. Now, for example, consider this example. See here, what is this 9850? That means see here, 0 is non-malware. So 9850 non-malware samples are predicted as non-malware samples. That is the thing you need to see here, actual predicted. So actual class label is 0, predicted 0. How many samples for that happened? 9850. That is the meaning. For 9850 samples, the actual label is non-malware. Your algorithm is also predicted as non-malware. That is the meaning. For 0 samples, actual is non-malware, algorithm predicted as malware. For 150 samples, actual is malware, algorithm predicted as non-malware. That is the way we need to analyze. And here you see the accuracy how we calculated diagonal 9850 by 10,000, 98.5. So by saying accuracy, you may misleading that yes, I got the accuracy of 98%. But what is the problem with this one is see, just see here, 150, what is that 150? Malware can be detected as malware. And that means all your virus files 150 are treated as non-virus. What happened then? Your model is not efficient. And see another way. What is this fourth column? So malware can be malware. How many? 0. That means even a single malware. Of course, total 150 samples of malware and 98550 non-malwares on your data set. In the 150 malware samples, your algorithm cannot able to identify at least one malware. That is the meaning. So here malware can be predicted as malware. How many? 0. All the malwares 150 are predicted as non-malware. That means all the virus files are treated as non-virus files. So is it, your model is good model? Definitely no. But your accuracy? 98.5%. So don't consider only accuracy, because in some cases this is happened in imbalanced data set. Generally, if the data is like malware or a heart disease detection, cancer detection, only the cancer samples are less samples. Most of the people are not having cancer. So only less samples, up to 10% to 15% are there. In those cases, if you apply algorithm, you will get this type of accuracy. Don't think that model is excellent. We will try to check this. How many
Hello, sir, Lakshman sir. Hello. Hello.
PowerPoint and come back in 5 minutes.
Okay. Okay.
Okay, and మనం 355 వరకు అలా కంటిన్యూ చేద్దాం లాస్ట్ ఇయర్.
Okay.
ఓకే. Sir, are you able to hear me?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Okay, sir. Sir, just make me a presenter, sir.
Yes. Yes, sir. You can start.
Okay. So what is the precision and what is the recall? But only the accuracy is not sufficient, as we discussed in the previous example. Consider a malware or a virus or a cancer detection. There are very less number of samples available as samples, cancer as samples. So that's why we need to focus on precision and recall. So what are all about this precision and recall? Precision tells you how many selected items are relevant, and recall tells you how many relevant items are selected. That's why you need to also consider this precision and recall. So in finally, what is the important measure we use to evaluating classification algorithm is accuracy, precision, recall. You need to see these three for each and every algorithm. Then only you justify the algorithm is good or bad. And this is the way to calculate all these. Simply use classification underscore report, which prints your precision, recall, and F1 score is also another measure which is based on both precision and recall. And confusion matrix you can use by using confusion underscore matrix, and accuracy score also you can see. We will try to see one example program. But see, the data set which we used before, that is the data set which we used for regression algorithm, is not possible to use here. What is the reason? In regression algorithm, we are predicting a number, but in classification, this is a category. So that's why I am using another data set which I downloaded from UECI machine learning repository. So I try to open the data set and I will show you what is this data set. See, try to open this data set and I am showing you what this data set contains. So this is a data related to bank. Of course, by seeing data set, it is very clumsy. It is difficult to understand what is happening. All the values are in single column, but not a problem. We will try to see. Getting this one, the data is related with the direct marketing phone calls of data banking institution. The classification goal is to predict if the client will subscribe a term deposit or not. So the variable name is also given Y. So Y means here yes or no you need to predict. That means whether that's participant or the customer make a deposit or not. Yes or no we need to predict. So here this answer is yes or no. So this is automatically a classification problem. So how to apply this classification problem with logistic regression? I will try to show you as I explained the logistic regression and the measures. Now it's time for the practical thing. We will try to see how to apply this logistic regression. So only the 3 lines of code changed. So no need to worry about the remaining code. That's why I spent some time in the morning session for coding. So the remaining things, all the things which we used, the encoding, missing values handling, all these are same both for classification and regression problem. But see, this data set is what happened. See here, all the variables are in single column. Okay, but separated by semicolons. These type of data sets are also available in the net. So to open this data set, what we will do, I will try to show you how to open this. Simply use delimiter. What is delimiter? You need to specify. So delimiter is equal to semicolon you put. Okay, so you put delimiter is equal to semicolon, then it opens like a normal data set only. I will show you. Try to open. See, it is opened like a normal data set, but actually all the values are in a single column separated by semicolon. Actually, simply use this separator. This is a delimiter. Delimiter is an additional argument you need to pass. Okay, but in this data set, some are not useful values actually. Where I removed some imbalance values are also there. I am removing them. Okay. So for that we need to do the same thing which we used, but here I dropped 4 variables. What is that? C contact, month, P days, P outcome. Why I removed? Actually, those are not having proper values. I removed. Out of 17, only 13 remaining. Then you know the remaining story. These are categorical features are there. See, this job is categorical feature, marital status, and education, default. So I need to apply one hot encoding by counting the column numbers 1, 2, 3, 4, 6, 7. These are the categories. I applied categorical encoding. So the concept which we discussed during the morning session. And after that, I divided it into dependent and independent variables. Now y contains only yes or no actually. Okay. So I have done it. And let try to divide it into training and testing set. And then apply your linear regression, logistic regression algorithm. And now try to see the predicted value and open and see what is this y underscore pred. It can predict no's and yes, not the values, not like numbers. Okay, so this is the y test. So this is the actuals and these are the predictors. So the same type of comparisons you can done. And as I told you, all the measures, these are the metrics we use, classification reports we need to use. I will show you the accuracy, all those things. It is executing. See, this is the precision recall. So precision for no class is 0.90, precision for S class is 0.56, precision for no class is 0.8, precision for S class is 0.17, and accuracy is 88.69. So this is the way to analyze. You need to consider all the precision and recall and class-wise precision also we get. As I am saying, this is a not good model in my opinion, because this is 90% and 98%, but this is only 56% and 17%. So this model is not good, even though I got an accuracy of 88%, but still it is not a good model because 0.17 and 0.56 are not good. Okay, so this is the evaluation, how to evaluate the model. So this is the logistic regression. Now we will try to see some more algorithms. This implementation I have already explained. Cross validation. So what is cross validation is, why we need cross validation? We will try to see. This is also very important. For example, this blue bar you consider as a data flow. What we have done up to now, divide it into training and testing set. This is a random split actually we are doing. The problem with the random split is, see, for example, consider the same sample we are using with yes sample 7, no samples 3. For example, I done a random 70-30 split. Then there is a possibility that all the S samples are in training set, all the no samples are test set. Then what is the problem here? All your training are with S only. If you give the output with no sample, how can your algorithm predict? That means training is not happened on the no samples. But if you try to do a test on the no sample, your algorithm unable to predict that. So that's why definitely there is a problem with random split. Then we go for cross validation. In cross validation, what we will do? Simply we will try to do all the parts are used as a both test set and training set. Here this yellow part is test set in first iteration, second iteration this part, this part, this part. So overall this is a four-fold cross validation. That means you divide it into 4 parts, and in each time every part of your data samples are treated as test samples. Generally this can be anything. That can be a 5-fold cross validation, 10-fold cross validation, and later we apply our algorithms. So this is the thing happened. These are the training data and test data divided into 5 folds. In first split, this one test set, second this is test set like this. And once again, there are number of methods for this cross validation, not only single one, k-fold which I explained. So repeat this process until every k-fold serves as this test set, and then take the average of your record scores. That will be the performance metrics. That means what happened is those type of unbiased is not there. All the S samples, all the no samples are considered in test set. So that's why there is no chance of that problem with the random split. So this is a k-fold cross validation. There is another variant called repeated k-fold. That means we repeat this step, for example, any number of n number of times. That is called repeated k-fold cross validation. There may be also another one called leave one out cross validation. Each one sample can be considered as a test set, and all the remaining training set. There may be also called stratified k-fold cross validation. This is a very good cross validation technique. If your data is having large imbalance, it will try to see every class is in test set or not. There are another model like repeated stratified k-fold, group k-fold, shuffle split. So number of methods are there, not only single method. So these shuffle split, see what happened here, not the continuous test set. See here, 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 here. So by splitting, all the test set is taken. In the second also randomly it will take the splits actually, not the continuous one.
Excuse me,
So
sir.
these are all
One
the
question.
different.
Sir?
Oh, okay, sure, sir.
Differentiate
Sure,
between
sir.
validation and testing, sir. So differentiate between
What, sir?
validation and testing, sir.
Difference between
Validation and testing.
Validation is actually, see, there are three sets we call as training set, validation set, and testing set. So in the training set is given for defining the model. In the validation test, it also checks whether the training is done in a proper way or not. That means before giving to the test set, actually validation set is used. Actually in VECA, if you are using VECA, the validation set concept we are using. But generally, if you are using any applying an algorithm nowadays, generally we go for only training set and testing set. Whenever you are applying cross validation, what happens is, as I told you, it divided into different subsets. So it also includes the validation set, because as I told you, see, this is a first set. In the first split, for example, all this is training set. So the test set is nothing but the validation set. Now here, this is actually also works as a validation set. Actually, the training, validation, test, the three type of data sets we need to create. But this practice is now we are restricted to the two only. But internally, the validation test, if you apply cross validation testing, that validation can also be done in the cross validation phase. Okay, sir. Hello.
Yes.
Okay, sir. Thank you. Okay, so now this is simply a cross validation. When we use cross validation, means your data is having a good labeling. For example, 50% as 50% no. Just the train test split is okay. That is random split. But there is a bias. That means imbalance misclassification is there, or unbalanced data is there. More samples of yes and less samples of no. In those cases, try to apply cross validation. Apply random split and see the accuracy, apply cross validation and see the accuracy. And see, this cross validation is also applicable in both regression and classification algorithm. This is splitting method. So irrespective of classification or regression, you just apply this cross validation above regression or above classification algorithm. So we will try to do this in for the same problem which we discussed. We will try to do at least two of the cross validation techniques. Okay, so consider the same data set which we used, the data set where we used for the logistic regression, the same story I am using. But you observe here, I am not using x underscore, y underscore, x test, train test split. This is the repeated k-fold cross. Actually, here I am using the Python for loop actually. But here, okay, no need to worry about all those things because you know the concept. As the repeated k-fold contains number of repetitions, I need to give how many repetitions. This is how many folds. So 3-fold cross validation 2 times. So that is the meaning. So for that, I am using Python indexing actually. Of course, no need to worry about that. I will execute and show you how the splitting is done. See, this is the splitting is done actually. So in the training set, first 0 to 45210 samples. See here, total samples 45211 rows. And in testing set 1, 3, 4, these are the testing set row numbers, training set row numbers. And in the second time, some 1, 2, 4, 5, 0, 2, 7, and randomly some 0, 6, 9. These are the testing samples. In the third time, so these are the training, these are the testing. So total 3 into 2, 6 times this is done. As I told you, this is a 3-fold cross validation 2 times. So 3 into 2, 6 times this is done actually. See here, that is this one, 1, 2, 3, 4, 5, 6. Of course, you can do it any number of times. So, but before giving the finalizing the model, it consider the evaluation or performance in each and every split. The algorithm consider the performance in each and every split. So now also you are having training and testing data. The difference is here we applied repeated k-fold cross-validation techniques. Okay, of course you can use the same code. See, the advantage here is this for loop is not changed actually. Okay, only the above two lines change. For example, if it is a k-fold, see, observe this thing. In the place of repeated k-fold, just use k-fold and arguments change. In the k-fold only you need to give how many folds? 3 fold. But there is no repeated, so only random state is there. I put it as none. Only the second line arguments change. It can be stratified k-fold, you can apply. So as the diagram I the PPT, all those are the actually classes available in Python. You will try all those things actually. Of course, you may go for at least 1 or 2 cross validation techniques and check accuracy. You will try to do random split and check accuracy, but you can also do cross validation and check accuracy. If both are good, okay, you are doing in a right way. So after that, you will apply the algorithm. The story is same. No need to bother about that, and check the while I used the same problem, I am checking the accuracy, the same accuracy I got or not. Okay, like that we will do it. So checking 88%. I think in the previous also we got 88%, and the same results we got. Okay, nothing changed. 90, 98. This is also 57 and 17. We got 90. So that means okay, your model is working in a correct way. The results are satisfactory or not, that is second. So there is no imbalance. We concluded because we use cross validation, there is no imbalance. Okay, so that is cross validation. Of course, I am not using. I not use for the regression algorithms. Just in the place of the try and test split, you just replace this code or this code and will execute that. Okay. But this is very important, especially if you are doing the research. You need to see this cross validation also. So these are the repeated k-fold and k-fold are the classes used in Python. This is the Python indexing. I am not going to deep because all of you may or may not have heard of Python. This is simply subscripting with Python, dividing it into the parts. Now coming to KNN, it is the easiest algorithm actually. Theoretically, it is easy. For example, there are 2 classes are there. What is our task? We need to divide it into 2 classes, green and red, and I have given a new category and asked you to put this data sample into either red or green. So that is the thing. For all the test data, we need to classify that into a class 1 or class 2. So we need to identify the k nearest neighbors. That means, for example, this is the point. Identify k can be a 2, 3, 4, 5, we will change. So for example, k is 4. Find 4 nearest points. For example, I considered a measure called Euclidean distance. So how to find nearer or not? There are number of measures are there. Euclidean distance is one of the measure I am using, for example. So find the nearest neighbors. For example, consider in this case, I selected k as 5. So these circle 1 are the 5 nearest neighbors. By using the Euclidean distance, I calculated distance. Now it is very simple. In these 5, so majority are for red class. So 3 are in red class, 2 are in green class. So assign your data point to red class. Okay. So assign this new data point to category 1. If equal, you may decide because 50% probability to that class and this class. You may think like that. But the story happening in KN is so simple. Find the k nearest neighbors. In the k nearest neighbors, majority of the neighbors are in which class? Apply your data point to that class. See, that is the actually the story behind this k. So implementation also, I will move on to the implementation. Very simple. I will try to show the code, executing the code. I think now you are familiar with the code. It is not so much difficult after seeing all these implementations. For example, it's the same example bank. I am trying to once again set current working directory. So if KNN it is calculating distances, generally it takes some time. If our data contains more samples, it will take some time. See, it is taking some time. I think I executed. It is taking some time. So we will come back here. Before that, we will move on to the PPT. We will discuss something and later come back here. It is executing actually. Support vector machine. As I told you, the support vector can be used for regression and classification, and the same concepts are same. There is a hyperplane is there, not a line, and this hyperplane and support vectors which are used to draw this hyperplane. And one more thing is important thing is that we already explained in the regression. The support vector machine can able to divide the non-linear data. See, if the data points are like this, okay, you can draw a line or hyperplane, whatever, it may be easy. But how you separate these 2 points, red and green points, if the data is like this? Is it possible to draw a line or a hyperplane? Not possible. But in those cases, we used those kernel functions. We used that kernel is equal to RPF in the morning support vector regression, I told you. So some functions are there by which we can even separate these red and green points. So it is actually not possible. This is called linearly separable data because red class, green class, some separation. Here there is no separation there. It is not possible to draw a line. But how to handle this? For that, actually, we are using some functions. So is it possible? What we do is take non-linear data, map it into higher dimension, and get your linear separable data. So by these statements, these 3 statements, you may wonder how we take non-linear data and map to higher dimension. Then how will we get the data which can be automatically separated? Yes, it is possible. Actually, I will show you a simple example. Consider these 9 data points. For example, some 6 red points and 3 green points, whatever it may be on the x-axis. If you apply x minus 5, what happened? So that means subtract 5 means each and every point 5 moves 5 positions to left. That is the meaning actually. These are actual points. I applied the function minus 5. So these points comes to left 5 points, 5 positions, every point. So this is f equal to x minus 5. Similarly, if you apply f is equal to x minus 5 whole square, then the data is now, see here, the data is like this. Now, so it moves up and now you can draw a line. Of course, this is not actual data points, but what happened? You have taken your actual data and you apply some function, and with that function, you can able to separate, that is the internal data. So applying some function definitely gives us some probability to divide the data into some classes. So that way, some mapping functions are used actually. So that is a simple function x minus 5 whole square, but in machine learning we used different complex functions like a kernel function, etc. So mapping function is needed. So then it is separated actually. The actual data, after applying the data, it may be changed, but the same function we are applying, this is also the actual data. Okay, so then internally what you have done, you can able to separate also, okay, by applying the function. So this is one function. This is the most widely used function called Gaussian kernel or RBF kernel. So this is one function which I explained earlier. The functions, the number of functions are there. This is one function. Actually, some formulas are there. I am not discussing the formulas. See, you can change this margin also by using this sigma value. This sigma is used for changing this margin value. Circumference you can change. So you can separate these two also by taking 2 middle points. You apply L1 and L2. You can separate non-linear data. This is more complex non-linear data can also be separated. So there are a number of functions available actually, not only Gaussian, a sigmoid function, a polynomial function. So all the purpose of these functions is to project the data into another way and then separate the data. So that is the needed. We need, what is the classification means? We need to separate S samples and no samples. That is the requirement here. Okay. So you can do the same experiment here using SVM. I think our previous experiment still not completed. KNN actually takes a lot of time, especially if your data contains 45,000 samples, it is calculating the distance. Okay, not a problem. I will show you the execution. And we will try to discuss the next algorithm, and we will try to see the all algorithms at once, because you know the pre-processing all the things. Okay, we will try to move on to the next algorithm. Naïve Bayes. So Naïve Bayes is simply based on the probability. I think if you teach the data mining, you know Bayes theorem. So in the Bayes theorem, there is a formula called probability, conditional probability is there. And we use this formula and we apply this formula to our features and classes. This is class labels and features, and predict the new. So of course, we will see some examples for this Bayes theorem. Actually, I added some examples, but I am not discussing because I need to go to the last algorithm and I need to tell you what are the things we need to observe while applying the algorithms. So I'm not discussing. So based on the Bayes, straightforward. For example, we need to find either walks class or drives class. I got 0.75% probability for walks class and 25 for drives class. I applied walks class. Walks is red and drives is green, whatever it may be. So based on the probability. And actually here there are different distributions. The data can be distributed in a different way actually, normal distribution or multinomial, Bernoulli distribution. So all these are given as a parameters in Naïve Bayes based on the data distribution. And Naïve Bayes is simply based on the probabilities. Gaussian Naïve Bayes, as I told you, most of the data sets are in normal distribution way. Actually, while discussing quartiles and etc., we need to discuss the distributions and some mathematical concepts that I removed because this is only one day schedule. We are having the data in different formats. The most widely used in Gaussian distribution. So Gaussian ND is there, Gaussian Naïve Bayes. Simply use, okay, I will try to show this for another data set. For example, we used the bank data set here. I will try to open a new data set called as malware detection data set. So this is also a classification data set. And that means we need to predict the sample as a malware or a non-malware based on the given inputs. So this is the malware detection data set from the Kaggle. I will try to show you. See, now it is displaying its output KNN. It takes that much time. So actually, I am connected with the hotspot. That may be also another reason it is slow. As the power is there. Okay, I will. That's why I'm try to download it. Or actually, the data set is downloaded. I will show you as it is downloaded. It's not a problem. So it is showing the output. Before that, we will see this data set. So see, the data sets are not different. Of course, there may be having missing values, etc. But the applying algorithm and knowing the background is the important things. Whatever may be the data set, code is same. Only the dependent variables and independent variables changes. See, this is the data set. You need to find what is the dependent variable actually. The dependent variable may or may not be last one. Here, the heading classification, here given malware. That means malware and non-malware. So here this is given as this in this column. So don't think always the last one is the dependent variable. Try to put filter. See here, benign and malware samples. Benign means non-malware. Benign is nothing but a non-malware sample. So based on all these parameters, as I told you, blindly don't apply the algorithms. If you are doing research, you need to know malware detection problem. You need to know about each and every of this feature. Without knowing this feature, it is not possible to apply algorithm. Of course, you can apply and see the output. That is there is no use. You can justify why these variables are used. As I told you, you can identify the outliers. Like this, you do some analysis. Before that, you need to know complete description about all these features. You must have complete understanding about your problem. Okay, but for showing you how we can apply the concept of any problem, I am using different data set. But before applying, you need to have some knowledge on all the features. Okay, so still it is displaying. Okay, not a problem. So we will see how to write the code. Simple, whatever it may be. I'm dropping some columns, so those are not useful. Hash and millisecond I am dropping. But see, you may ask, sir, why you drop? There is no rule. You may consider it not a problem, but if you consider it, it consists of more missing values. You can handle more categories. You can handle. You can do pre-processing. That all comes into pre-processing. So I divided into dependent and independent variables and splitted. And feature scaling can also be applied. And Naïve Bayes, there are different algorithms, models in Naïve Bayes, Gaussian and the one which is the popular one, as I told you, normal distribution. Simply the same thing, create an object, fit into your data, predicting using the model and seeing the results. So the same thing, confusion matrix. But I will also show you the confusion matrix in the logistic regression also. I have not shown the confusion matrix. Actually, see here, KNN takes this much time. Finally, you got results. So actually, I had both classification training accuracy and testing accuracy. I done it. See here, it is good to compare both training accuracy and testing accuracy. Sometimes what happens, your training accuracy is good 90%, your testing accuracy is only 50%. So for that, you will also check training and testing. How to check training accuracy, testing accuracy? Yes, in the formula, see here, you will give train data. That means, see here, Y train and X train, confusion matrix for Y train and X train. That is for training data. Similarly, classification report for predict of X train and Y train. Similarly, for Y test and Y predict is nothing but the testing. Testing accuracy is always nothing but Y test Y predict. That is actual predicted. So classification report for Y test Y predict gives testing results. And if you applied for Y train and predicted of X train, you will get training results. So it is a good idea to check both training accuracy and testing accuracy. Now see here, this is 91%, this is 88%. There is not much difference. If this is 91 and this is 60, that is nothing but the model is not good. Okay, so there is a less difference between training and testing accuracy. We used the term overfitting and underfitting accuracy. What is overfitting means? If the training accuracy is 99, testing accuracy is 50. That means, okay, in the training, very good, excellent, overly fitted. But when you go to testing, it is poor. That is called overfitting. Underfitting means in this training accuracy only you get some 40%, 45%. So then what is the need to go for testing? So initially it is underfitting. So you need to check underfitting and overfitting also actually. Okay. So this is the KNN actually. We will move on to KNN with different data set. Sorry, Naïve Bayes malware detection as I discussed. So the application of algorithm is same. First, I'm clicking it. Yes, you can also run the whole program by clicking it. Okay, see here the same results we got, but I will try to open the CM. Confusion here, confusion matrix is also there. Like this, it is shown in the variable explorer. That means these are the correct predictions and these are the wrong predictions. I created CM test and CM train. So see, this is for testing data. This plus this are correct predictions. These are wrong predictions. Similarly, for training data also. This is the way to see the confusion matrix. See, for all these, you are having a predefined classes. No need to worry about that. See, classification underscore matrix is there. Classification underscore report gives all these values. What are those? Disprecision, recall, all those automatically given if you just use the single line. That is enough. Okay, so once again, we check precision values, recall values. 0 is a non-malware, 1 is a malware. Accuracy is only 69 actually, not good. That means it is 70% accuracy. Not good. So if the accuracy is not good, what are the possible reasons? Yes, you can do a lot of research there. That is research actually. You need to find if there any outliers are there, and you need to find if the data samples are not enough. You need to add some more data samples, etc. Okay. So that is Naïve Bayes. So decision tree classification, as I told you, decision tree is used for both classification and regression. But while discussing the decision tree, as I told you, the major problem is how to find the root, how to find next child, where we use a measure called as MSE. I shown that example actually. Here I am not discussing. But here also the same problem. What is the root node? For example, consider this data set. This is a screenshot from NPTEL course actually. So you need to predict whether the player can play the tennis or not based on this humidity, outlook, temperature, and wind. So here you need to draw a tree, but what is the root node? This is again the same question. So here we use different measures actually. We use the measure MSE in decision tree regression. We used a measure called information gain or Gini index. These are the two measures, either this one or this one. If you use information gain, that is again based on another formula called entropy. So either information gain or Gini index, these are the two measures used to find the root node. So if the information gain is more for a particular variable, that becomes the root node. You do repeatedly and construct a tree. So I am not discussing that actually. Example actually I added, but I am not discussing the formulas. At least I will show you. So it is a formula. This is the formula for entropy. Here P plus P minus is positive and negative samples, S and no samples. And this is the formula for gain. Okay. So based on these formulas, you find the root node. Okay. Once again, you repeat the same process. You find the errors, repeating. So the same story. So once again, you apply the same for another data set, cancer data set, you apply. See, I'm not showing the practical thing now because we are going to conclude the session. Application is same. Coming to random forest classification, the same thing. In the previous random forest regression, you take the average as I told you, but here you take the voting. Voting means, for example, in these two says answer is yes and this one says no. So majority says yes. That's why the answer is yes. So that's why here we use majority voting. How many are voted for yes? How many are voted for no? Majority is yes. Output is yes. Majority is no. Output is no. So this is very simple. Okay, when coming to random forest regression, you will take the average because that is the number. You will take the average of tree 1, tree 2, and up to tree n by total number of trees. But here you need to take the majority voting. That is the difference. Here also the same story. You can put any number of trees that can be 1 to n trees, 1 decision trees. But here all are decision tree classifiers, not regressors. Okay. Once again, you can do the experimentation. And ensembling means actually there are 3 techniques in the ensembling: boosting, bagging, stacking. Okay, so these 3 are the different types of ensembling. One example for boosting is the gradient boosting algorithm, and random forest is an example for bagging algorithm. Bagging in the sense combining same algorithm of different types. Okay, so stacking means you can combine different algorithms. I combine one KNN, one SVM, one logistic regression. That is called stacking. You can combine any number of different algorithms, that is stacking. You can combine any number of same algorithms, that is nothing but the bagging. So in the random forest, we combine 1 or n decision trees. But in stacking, you combine different algorithms. It works in the same way actually. Of course, in the ensembling, voting, and stacking, different flavors are there. But the major difference between bagging and boosting is this is parallel, this is sequential. That means, see, first you applied first model, take the output, second model, third model, like that. But this is parallel. You applied first model, second model, third model independently. So that's why this bagging is random forest. Decision tree 1, decision tree 2, decision 3 independently take the average or the majority voting between regression classification. But here, after implementing first one, then that is given to next algorithm, that predictions, then second one, then third one, like this. So this is sequential and that is parallel. That is the major difference between the boosting and bagging. Now coming to research scope, different problems are available in machine learning field actually. As we shown, temperature prediction, energy prediction, these are regression problems, and classification problems are there, image or fingerprint recognitions, video processing, the banking of medical research, disease detection, the heart disease, cancer, business trends. You may use recommender system sentiment analysis, actually deep learning we are using, and in cyber security, which we used in malware detection example. Similarly, speech recognition, NLP, and text-to-speech recognition. So there are a number of applications you can develop. There is a lot of rich scope in machine learning. But the problem is there are also equally challenges are there. Data pre-processing is the major challenge. That means without doing data pre-processing, you will get poor results. Scalability, that means you do for 1,000 rows. If you increase to 10,000 rows, is it work? Or if you do decrease the size, is our algorithm work? Yeah, so try to see the scalability, dimensionality. As I told you, it's actually there are a number of other concepts are also there, but in one day it is not possible to cut off dimensionality. For example, your data set contains more and more number of columns, it will reduce those. That is dimensionality. And if the data is complex and heterogeneous data, so that means combination of different types of data, and data quality is there, privacy is streaming. So all these you need to consider. And these are the data sites where we available. I will share this PPT links, virus data sets available in this link, and Kaggle, KD Nuggets, Line Bridge, which I shown, and UNB. What is this? This is nothing but UCI repository. Okay. So I think with this, I am concluding my sessions. Still, I will wait for 2 or 3 minutes. You are having any doubts? Even you can also put the doubts through the mail. Not a problem. Just note down my mail, and you can also ask the doubts with the mail. I will clarify it. Okay. Thank you.
Thank you, Lakshman Rao sir. So thank you very much for your wonderful presentation. Sir, can you please share your PPTs to the participants?
Yes, sir. I will try to reduce because there are some other slides also. I will share by tomorrow, sir. In the WhatsApp group only, I will put it by doing some modifications.
Okay, because many participants, they are highly interacting with the resource persons, and probably because of shortage of time, they may not be in a position to interact with you. So can you contact, can you help them even after this session in case if
Yes,
they
sir.
have?
Not a problem. Yes, sir. No problem. Not a problem. We can contact anytime.
Yeah, I request you to take up one or two queries from the participants, if possible.
Hello.
Hello.
Yeah, good evening, sir.
Sir. Okay. Tell me.
Yes, sir. I just gone through like what are the data sets you use. It's amazing compared to yesterday's session. It's again a more practical one. So I'm really happy with that part. Sir,
Okay.
as organizer, sir has already asked you to share the PPTs. Are you going to share your email address, sir, so that in future we can communicate with the?
Yes, sir. Yes, sure. And
Uh,
actually, the image also we can see. For example, in the I have one more session actually Friday. In that I will
okay.
discuss some deep learning. In that we will see CN and RNN actually deep learning
Mm,
implementation. So this is
okay.
my email ID, sir. Lakshman1216@gmail.com.
Okay, fine. And sir, the code that you have demonstrated here, are you going to share that part with us?
I will share, sir. Whatever the codes I explained, I will share.
Okay, then it will be fine for us because, like sir has told, that having limited time and exploration is not that much kind of thing to be done in the session. But we can try at our level, and if we have doubt, surely we'll contact you. Thank you, sir.
Okay, sir. Thank you, sir. 355. 355.
Okay, sir. Any more doubts from the participants?
Hello, sir. So the main theme of machine learning depends on data only, no, sir.
Yes, sir. Yes. The data is good. Yes, sir.
Uh,
It depends.
Suppose
It
data is
depends
got
on
some.
data only. The data is hello.
Suppose data has got some defect, then our model may not be correct, no, sir. Whatever the algorithm you apply, that may not give the correct result. Data is not corrupted.
Actually, there is hello. So actually, there is no rule of thumb, sir. You select the data. For example, if you are doing the cancer prediction, you may go for CAGIL or UCI, or you may take the real data from hospitals. So based on that, you create the data processing. So data processing takes some time, sir. Actually, that applying the algorithm is a big thing. Okay. Sir, Samsura, sir.
Yes, sir. Sir.
Hello.
Yes, sir.
Samsi, the email address because so if you are having any doubts, just mail me or put in WhatsApp. My WhatsApp number is there. I will definitely respond. Okay, and I am also having a session on Friday. If you are any doubts you are having, we will discuss those doubts in first 15 minutes and then move on to the next topic on Friday. Okay, sir.
Yes, sir. Yes, sir. Sir, you are also available in the WhatsApp group.
Okay, sir. Okay, thank you.
The participants can ask you.
Yes, sir. Yes.
So
WhatsApp group. Okay, sir. Okay, sure.
yeah. Thank you, sir. Thank you very much, Lakshman Rao, sir. You have spent
Thank you.
your valuable time.
Thank you, sir.
For
Thank
our
you.
participants.
Thank you, sir. Thank you so much.
Thank you very much,
Thank
sir.
you, sir. Thank you.
I just want to comment one thing for the organizers, sir.
Yes, sir.
Yeah, this is one of the I think only one STTP where or like experts are in the WhatsApp group.
Yes.
Other in other STTPs we found the organizers, but not experts are there. So it's really good, sir. Thank you very much, sir.
Yes, sir. Yes.
Thank you, sir.
Sir, one question, sir. One simple question. Sorry for last interrupting.
No, sir.
Lakshman, sir.
Yeah, madam, please. Tell me.
Hello.
Madam.
Yes, sir. Many people follow this Jupyter notebook spider. Which one is? Hello.
Yes, madam, please tell me.
Yes,
I
sir.
think
Sir is here,
I
sir.
think sir has left the session.
Okay, okay, no problem, sir.
Probably you
Take the
can post your this thing query in the WhatsApp group, madam. He will respond.
fine, sir. Okay, sir.
Yeah, madam.
Thank you so much. Thank you. Okay.
So with this, we will conclude our session 2, and tomorrow we will have session at 10:30. So kindly join. So thank you all.
Thank you, sir.
Thank you.